Alright, hey everybody, so here we go with our last video for chapter 8. So this video is on the fundamental theorem of calculus. Now hopefully that sounds familiar because we've talked about the fundamental theorem of calculus part 2 already. So hopefully you remember that we used it when we were evaluating integrals. So the fundamental theorem of calculus part 2 tells us that the integral of a function is equal to the antiderivative evaluated at the upper bound minus the antiderivative evaluated at the lower bound. So we use that in order to actually evaluate integrals, and we've been doing that for a while now. Well, the fundamental theorem of calculus has another part, all right, and it's what helps us look at problems like this, where we have to take the derivative of an integral. So let's talk about what actually happens there. So we did a little bit of this in class today with some experimenting with some things. So let's do one just to kind of refresh our memories. But we're going to leave this derivative part alone. So I'm going to go over here and I'm just going to write d dx. Or I'm sorry, d dx is what I said, but not what I wrote. So we're going to just write that. And we're going to focus on actually worrying about this integral first. All right. Well, we know that the integral means take the antiderivative. Well, the antiderivative of cosine is sine. So we're going to do sine of t plus c, and we're going to evaluate it from 3x to x squared. So again, we're going to leave this derivative part alone, so d dx, and we're just going to focus on this integral for a second still. So sine, and we're going to evaluate at the upper bound, so sine of x squared plus c minus sine of 3x, that's our lower bound, plus c. All right, and then when we simplify, we remember the c's always cancel. If we distribute this, yep, that'll make sense. So inside here, we're going to have sine of x squared minus the sine of 3x. And now we're going to actually take the derivative. But if you notice, everything I wrote in blue was really just focusing on that integral and taking the antiderivative and then evaluating it. By the way, that's the fundamental theorem of calculus part 2, right? When we evaluated the upper bound minus the lower bound. Okay? Now let's actually take the derivative. So the derivative of sine of x squared, we know that that's going to end up being the cosine of x squared, but now we need to worry about some chain rule because we've got the x squared on the inside. So the derivative there would be 2x, and then minus the derivative of sine of 3x would be the cosine of 3x, and then we're going to multiply by 3 because that's the derivative of 3x. So if I go ahead and just kind of rewrite this nicely, we're going to have 2x times the cosine of x squared minus 3 times the cosine of 3x. All right? But here's the thing. I don't want to do that every time because that's kind of annoying to have to take the antiderivative and then take the derivative. So let's kind of look and see what's going on here. So hopefully you guys notice that we started with a cosine function. We also ended with a cosine function. All right, so this original function here is still in my answer. And that should make sense to you because we took the derivative of an integral. All right, it's kind of like adding 5 and then subtracting 5. We get back to the same thing we had because they're inverses of each other, right? So derivatives and integrals, they undo each other. So if I undo it, I should still get back to the original function that I had. But now what I want to point out to you guys, and hopefully you can already kind of start to see it, but take a look at your upper bound. Your upper bound is x squared. And if we look here, inside the cosine function, the first thing that comes is the upper bound. That's my x squared. All right, and then the lower bound is 3x. And we can see that the 3x is right here. It's cosine of 3x. So we took our original function, which was cosine, and we evaluated it at the upper bound minus the lower bound. Now the only new pieces here would be this 2x and the 3, but hopefully you can see the derivative of x squared is 2x. So this piece here was really just the derivative of the upper bound. And the 3 that we have here, I'm going to draw an arrow so we can kind of write it over here. But the 3 is the derivative of the lower bound. Which means hopefully there is a way for us to do this without having to do all of these steps every single time. So that's our big idea here. Can we create a rule that will allow us to take the derivative of an integral more efficiently? And the answer is yes. So let's take a look at what this would look like. We want to take the derivative of this integral evaluated from a to b of f of t dt. Well, we already decided that whatever that original function is, that function has to stay. So, since this original function was f, my function f has to stay. So it's going to be f of something, and then we're going to subtract f of something else, because that's my cosines here. All right, and we know that the upper bound is what's going to come first. So this is going to be f of b. And the lower bound is what's going to come second. So this is going to be f of a. But we know that this wasn't just cosine x squared and cosine 3x. We also had these other parts here. We had the derivatives of the upper and lower bounds. So we need to include that here. So once we do f of b, we need the derivative of b. So we're going to just write that as db dx, because that's the derivative of b with respect to x. And then we're going to need the derivative of a with respect to x. All right, it looks a little funny, I know, but in practice it actually makes a lot of sense. And as we do problems, it kind of all comes together. All right, so let's see what some of these problems actually look like. And let's do the shortcuts so we don't have to do all this work that we did here. We are not going to do all of these problems, obviously, because there's a lot on here. So we'll save some of them for class so we can kind of start class together. All right, so let's see. We are asked to find the derivative of the following functions. Well, you'll notice all the functions that we were given are integrals. So our original functions are an integral, and we're asked to find the derivative, which means when we start to find dy dx, we're really doing the derivative of this integral. All right, well, we just said if we take the derivative of an integral, that we're going to keep the same function. So sine, and we're going to do t squared, but instead of t, we're going to plug in the upper bound. So in this case, we would have x squared. And then we need to multiply by the derivative of the upper bound. The derivative of the upper bound is just 1. And then we're going to subtract our same function, which is sine, but now we're going to plug our lower bound in for t. So we're going to have 4 squared times the derivative of the lower bound, which is 0, which means dy dx is really just equal to, in this case, the sine of x squared. So this second piece cancels out because the derivative of 4 was just 0. All right, but you can clearly see when we look at this piece, here's our original function, right? It was the sine of t squared, so it's the sine of upper bound, x squared, lower bound, 4 squared. This 1 was the derivative of our upper bound, and the 0 is the derivative of our lower bound. All right, let's take a look at number 2. So you'll notice it's actually the same function on the inside. All we did was change this upper bound. But you should notice that it's really kind of different. So we are going to have to apply the chain rule here because now we don't just have an x to take the derivative of. So we know that dy dx is going to equal the derivative of this integral. So 4 to 3x squared plus 7x sine of t squared dt. All right, so let's see. I'm going to come over here so I make sure I have enough room to write all of this. But we're going to do the sine evaluated at the upper bound. So that's going to be the sine of 3x squared plus 7x squared times the derivative of the upper bound. So the derivative of 3x squared plus 7x would be 6x plus 7. And then we're going to subtract the function evaluated at the lower bound. So we're going to take the 4 and plug it in. So we would have 4 squared times the derivative of 4, which is 0. So again, that piece ends up canceling out, which is kind of nice. And we end up with dy dx is equal to, I'm going to just bring this in front. So I'm going to make it 6x plus 7 times the sine of 3x squared plus 7x squared. So hopefully, even with just these two problems, you've noticed that if one of our bounds is a constant, then that piece is always going to go away because the derivative of a constant is 0. So it's always going to fall off. All right, so let's take a look at number 3 just really fast, just to take a look at what happens there. So dy dx is equal to the integral, how about the derivative of the integral, 3x plus 2 to 7 sine of t squared dt. So again, same function, so we should kind of be okay with this so far. So we're going to use that same function, sine evaluated at the upper bound, so now the 7 squared comes first, times the derivative of 7, which is 0, minus sine of, this is going to be 3x plus 2 squared, times the derivative of 3x plus 2, which is 3. And now you'll notice that the 0 is actually what comes first in this one, because that was our upper bound. And so now we get that dy dx is equal to negative 3 times the sine of 3x plus 2 squared. Now you'll notice this is the only one that's been negative so far, but that's because on the other ones it was our lower bound that went away and became a 0. On this one, it's our upper bound that's the constant, and so that is why this ends up becoming a negative here. All right, think about switching these bounds. If we were to evaluate this from 3x squared plus 7x to 4 instead, this would end up being a negative answer. And same thing here, if we were to switch these bounds, this would become a negative, so it would end up being a positive derivative instead. Okay, let's take a look at one example where we actually have bounds that are both functions as opposed to having a constant. And then we're going to move on to the next part of the fundamental theorem. So we should be pros at this by now, but the derivative with respect to x is going to be the derivative of this integral, so 2x to x squared, of 1 over 2 plus e to the t dt. Now if you guys want, you could pause the video and then play it and fast forward to the answer and see if we match, to see how you guys are doing with this, but hopefully you're doing all right. So if we take the derivative of the integral, we need the same function, so 1 over 2 plus e to the upper bound, which is x squared, times the derivative of the upper bound, which is 2x, minus 1 over 2 plus e to the lower bound, times the derivative of the lower bound. And then we're going to go ahead and simplify. So dy dx is equal to 2x over 2 plus e to the x squared minus 2 over 2 plus e to the 2x. And that is our final answer. Now be careful here. Don't get cancel happy and start canceling a bunch of 2's. That doesn't actually happen here because this has a plus on the bottom. All right, so no